Okay, it is 1 o'clock, and I'm broadcasting live from an undisclosed location. If you can see me, you know that I'm online. I'm going to change my name at the bottom here so you can see my Twitter handle. Okay, hopefully that'll work. There you go, that's better. So you can see my Twitter handle is @Dionandin, and I'm the master of time and space. So far, I have no viewers showing up on my feed. I'm assuming you are all taking your sweet time and logging on, or you're using the YouTube link and not the Google Hangouts link. Excellent. So today we're going to be talking about the chi-square again, point 2. And because the technology can be questionable at times, this presentation will be a lot like my intimate life, quick and dirty. Yeah, I said it. And I'm broadcasting from a secure, undisclosed location, which is either a bunker somewhere in Northern Ontario or my parents' house in Toronto. And if my mother walks through that door, then we'll know which one it is, and questions will be answered. Right. I have an incoming call right now coming out of my phone, and I'm going to skip that call. So in a second now, I'm going to switch to the sharing view so you can see the slides. And as well, this presentation is public. It's on YouTube, so we're going to get some people dialing in from all over the world who are curious, who see this bizarre face on their screens and are wondering, well, is this some sort of grotesque surgery demonstration? But that's not the case. Again, if you want to ask a question, tweet me at Dionandin. My handle is at the bottom of my name right here. I will try to monitor the questions on a separate screen over here as I go. I'm actually surrounded by 3 computers because I'm at work, and we'll see how it goes from there. As well, if you are having technical issues, meaning if you can't hear me, if the screen freezes, please someone tweet me right away. Anything that goes wrong today, I'll cover again in class live on Friday. Yes, excited? Pretty excited. Yeah, so occasionally I use this technology, Google Hangout, to run virtual office hours as well. And let me see if I can do some great effects here. Bear with me. If we're going to do this, you may as well make it fun. All right, so let me turn this off. Come on, you can do it. Ah, eesh. Okay. I'm trying to get myself a mustache. Come on, mustache, come on. Here we go. Let's give myself... Oh, that's it. That's better. Devil ear. Okay. That's more appropriate. Or maybe... there, that's you. No, hang on. No, I guess you're stuck with devil horns. Okay, so I'm going to switch now to the slide view, and you can see all the wonderful things I've prepared for you. So bear with me 1 second. Let me just make sure that everything's ready to go. We are on top here, and I share my screen. One second, sharing now. Okay, great. So right now you should be able to see this first slide in the chi-square part 2 presentation. If you cannot see that slide, let me know. Tweet me right away. Looking at my Twitter feed, no one's tweeted me. Everything is good. Yay! I love when technology works. Yay! All right, let's begin. So, last time we talked about how the chi-square works and the null hypothesis of the chi-square test. Remember, the chi-square test is what we use when we're determining whether 2 categorical variables are associated or related to one another. Okay, so the null hypothesis is that the 2 variables that we care about are not related. In other words, they're independent, or the proportions of the other variable distributed across the values of the first variable are more or less equal. That's what we mean by independent or unrelated. The alternative hypothesis is going to be that they are related, or that the proportions are somehow not equal, statistically not equal. To do this, we create a contingency table, and again, a contingency table is also called a cross-tabulation table, and the values on one axis are contingent upon the values of the other axis. That's why it's called a contingency table. In our contingency table, we place our observed values. This is our data. This is what we get from our study. That's what I would give you on an exam, for example. Here are the that's what we put in there. We use the chi-square methodology to compute the expected values. Quite straightforward, right? And then we apply both the observed and the expected values into the chi-squared formula to compute the chi-square statistic. We also compute the degrees of freedom, and we compare everything to the values in the back of the book. Just like we've done for everything else, like the ANOVA and the t-test, we just compute a test statistic and we compare it to the back of the book. So, some assumptions for doing the chi-square test. First is that our observations, our data, are somewhat randomly sampled, meaning I didn't cherry pick them from my larger reference population. The next is that they're independent, meaning that they're not related to each other in any systematic way. As I select one individual, that doesn't determine how the next one is selected, for example. Now, if they are dependent, we have another test, and we're going to look over that test later on in this lecture. It's called McNamaras test. But before we get there, the other chi-squared tests are independent. So each cell in the contingency table must have an expected frequency greater than 0. Remember, the expected number is what we compute. It has to be greater than 0. If it's not greater than 0, we have another test for that. Each cell must have an observed frequency, i.e. our data, what we actually collect, what I give you, what comes out of your study, must be at least 5 or more. If it's not, we have another test for that. Okay? But this is for the chi-square test. Now, the textbook might say that the cutoff is 10, but in my experience, most people agree that it's 5. Now, as I mentioned, there are lots of different tests that purport to do something very similar to a chi-square. And you may ask yourself, why? Why are there so many tests? Can't we choose one? And we can, actually. There's something called the Fisher's exact test, which does almost everything exactly, and it's done well, and it's much more robust to all these assumptions than the chi-square is. So why don't we use that all the time? We probably should, but these tests were invented before computers came about, and people like to have easy ways of computing things by hand. That's why on your exam, I'll have you compute chi-squared by hand, because we can. The chi-square formula is easy enough, we can do it by hand. The Fisher's exact test is more complicated. In the current technological climate, we can do these complicated things quite easily with the press of a button. But I think it's useful if we go back to first principles and we do things by hand, just so we understand what it is we're actually doing at a conceptual level. So remember, if the assumptions are violated, we have other tests to apply. If any of our observed data, again, the data that we collect, has fewer than 5 counts in any of the cells in my contingency table, we can use the Fisher's exact test. It's an exact test. It's not an approximation. A chi-square really is an approximation. Now, I'm not teaching you how to do the Fisher's exact test in this class. It's a complicated formula, but I want you to know when you can apply it. The answer is pretty much always. What happens if the expected value is less than 5? Remember, the expected value is what we compute as being what we would have gotten given a random distribution in our cells. If it's less than 5, that violates the chi-square assumption as well. We can apply something called Yates continuity correction. Again, we don't teach Yates continuity correction in this class, even though it's quite simple to do, but I want you to know when we would apply it. Now again, in practice, we can still use Fisher's instead of in situations where the expected value is less than 5. So why do we even bother with Yates continuity correction? We bother again because in the good old days we didn't have computers that made it so easy. So I want you to know about it for historical reasons and also to understand what we're doing here. So Yates continuity correction actually reduces the value of the chi-square. It makes it more conservative, and in that way we're less likely to overestimate the significance in our sample. Because if our expected values are small, that drives us towards rejecting our null hypothesis. So this is the formula for the chi-square. Again, I don't require you to memorize that, even though it's useful to do so. You'll have a cheat sheet on your exam, so you don't have to memorize this. And this is how the Yates correlation correction looks like, continuity correction looks like. It just subtracts 0.5 from the overall sum, and the chi-square form looks like this. Again, it doesn't matter. You don't have to memorize it. Write it down. Just be aware that they exist. Remember, the Yates correction correlation, the Yates correction coefficient, I'm sorry, I'm stumbling over my words, only applies to 2x2 and 2x1 scenarios. Chi-square can be any number of rows and columns, 12 by 20, 15 by 45, 3 by 5, whatever it might be. Most commonly, it's 2 by 2. But if it's 2 by 2 and 2 by 1, and we have an expected frequency less than 5, then we can apply Yates correction coefficient, or we can run a Fisher's exact test. So when can we use a chi-square test? We can use it in lots of scenarios. Some famous ones are like the seatbelt laws. You're probably too young to remember, but I remember back in the day, back in the 70s, when people weren't compelled to wear seatbelts, and when the seatbelt law was introduced in Ontario, I remember the big pushback by people. I don't want to wear seatbelts. If I get in a crash, I want to be thrown free of the wreckage. That kind of nonsense. So statisticians had to do some math and figure out, is there a relationship between seatbelt wearing and frequency of accident or frequency of death? So a potential research question would be, is the relationship between whether or not you wear a seatbelt and whether or not you die in a car crash, are those independent measures? That would be a null hypothesis. The null would be that they are independent. There's no relationship between the two. And a chi-square will be applied to determine if, in fact, that's true. So let's work through an example. The example here is from Sweden. It's a customer satisfaction and employee empowerment study. So we have a company, and they are measuring whether or not the satisfaction of their customers is in some way related to the satisfaction of their employees. More specifically, customer satisfaction, is it related to employee empowerment? And the assumption is the more empowered our employees feel, the better they treat the customers, and the customers are even more satisfied. So this kind of analysis would be used in a management context to determine whether or not treating our employees differently may manifest as better customer satisfaction and therefore presumably better customer loyalty. Excuse me, I have to take a glass of water there. All right, so this is how it worked. They had categories for each index: very low, low, moderate, high, and very high. So you can have, very low customer satisfaction, high customer satisfaction, and so forth. You can have low employee empowerment, high employee empowerment, and so forth. Now, the example I'm going to show you uses a chi-square to analyze whether or not there is a relationship between customer satisfaction and employee empowerment. What kind of measurement is this index? Is it nominal? Is it ratio? Is it interval? No, it's ordinal, isn't it? This is a ranking system. Very low, low, moderate, high, and very high. I gotta say, ordinal measures are not appropriate for chi-squares. However, the example I'm going to show you uses a chi-square to assess whether or not two ordinal measurements are related. So it's wrong. I'm going to show you an example that's wrong. If in the real world you come across an ordinal ranking that you want to measure association of, we use a different kind of test, a test called a Koskalwallis test, and we'll talk about that later on today. Recognize, though, that even though this is wrong, the actual math I'm going to show you is how you would do it if, in fact, this were not an ordinal measurement. So I'll say it again. Because this variable is ordinal, it's not appropriate for chi-square. Let's pretend, though, that it's not ordinal, and we're going to do it anyway. And I pulled this example off the internet, and the internet should be ashamed. Shame, internet, shame! So this is our data, and I apologize, Google Slides has sort of skewed the table slightly, but you can see what this looks like. Oh, hang on, I have a tweet here. What does the tweet say? The tweet says, okay, so this Maryse is retweeting me from ages ago because clearly she's not paying attention. Are you, Maryse? Okay. I've compressed the levels of the variable into 3 rather than 5. So low, moderate, high, low, moderate, high. This is therefore a 3 by 3 table. Right away, that tells you if I'm violating the the assumption that says I have expected values less than 5, I cannot apply the Yates correlation correction, because that only works on 2 by 2 tables, right? We have a 3 by 3 table now. Okay, that's great. And here are my data. What do I do with this now? Well, let's go back to our null hypothesis. The null hypothesis is that customer satisfaction is not related to employee empowerment. In other words, the proportions of empowerment across the different levels of satisfaction are the same, or statistically the same, right? I can't stress that enough. Some people look at the numbers and say, oh, they're clearly not the same. Why even test for it? Well, there's a difference between being the same and being statistically the same. Okay, so what we're saying here is that the levels, the proportions in each of these categories are essentially the same, or the groups are independent of each other, or the variables are independent, or satisfaction is not related to employee empowerment. Therefore, our alternative hypothesis is going to be that satisfaction is related to empowerment somehow. A new tweet I've received, someone is following me. Well, welcome, Maureen, you are now following me. Okay, note that this doesn't tell us the direction of the association. It just tells us whether or not they're different or the same, right? So if I determine that satisfaction is somehow related to employee empowerment, it doesn't tell me if increasing satisfaction means more empowerment or vice versa. It just tells me that they're somehow related. I'd have to do more nuanced and deeper investigation to determine whether or not there's a direction. So let us look at our data. We create our cross-tabulation contingency table. It always looks like this. Unlike when we did odds ratios and relative risks, it doesn't really matter which variable goes on which axis. It'll give you the same answer, right? So this is our data. These are our observed data. The observed data are the data that you collect from your study. Okay? And let's say it looks like this. What do I do now? I compute my expected data. Remember, the expected data comes from multiplying the marginals and dividing by the total. So for the first cell up here, the marginals are 41 and 32. I multiply that out and divide by 171. Okay? And I do that for the same for all of the cells here. And I get the expected data. And I get these numbers. So let's go back for a second. So here's my here's the original data, right? Oops, sorry. Original data, 13, 11, 8, and so forth. And my expected data is 7, 11, 12. So they're different, but they're not that different. The question now that the chi-square seeks to answer is, are they sufficiently different that we can say that, in fact, the distinction between observed and expected is so great that there must be some kind of relationship going on? So I take these numbers and I plug them into my spreadsheet. So for each of the 9 cells, and there are 9 cells because it's a 3 by 3 table, I have my observed values, I have expected values. I subtract each one and I square the difference. Remember, I square the difference to get rid of that minus sign. And then I take that square difference and I divide it by the expected number and I add them all up. And I get my total chi-square, which is 7.2. Now, do you remember what I do with that 7.2? Yes, you do. I have to compare it to something. I have to compare it to a number from the back of the book. And I get that number by also computing the degrees of freedom. Remember, the degrees of freedom is a kind of proxy measurement for the total sample size. And in the chi-square scenario, that's given by the product of the number of rows minus 1 and the number of columns minus 1. Here it is. In this case, the number of rows is 3. 3 minus 1 is 2. Number of columns is 3. 3 minus 1 is 2. I multiply them and I get 4. And degrees of freedom is 4. So for a degrees of freedom of 4 and let's say an alpha of 0.05, I look up the chi-square value in the back of the book and I get 9.49. Remember, my number was 7.2. My chi-square is less than the back of the book's chi-square, therefore I fail to reject the null hypothesis. Let's go over that. What was the null hypothesis? The null hypothesis was that there is no relationship between customer satisfaction and employee empowerment. Did we reject or fail to reject? We failed to reject the null. Therefore what? Therefore, customer satisfaction is not related to employee satisfaction, just like the null hypothesis said. Now, the same data can be processed by SPSS or any other stats platform, and this is how the output for SPSS looks. I'm assuming you can see my mouse moving across the screen. If you can't see that, someone tweet me right away and tell me. So the first box shows us just some diagnostics for the process. The second is the actual data that we entered. Right, employee empowerment in the top, customer satisfaction is on the left, and these are the data we entered. And the chi-square results are in the bottom box. Notice that the Pearson's chi-square value is 7.225, very similar to our number of 7.2. It's a bit different because they make slightly different assumptions, the computer does. 4 degrees of freedom, and they computed a p-value of 0.124. Notice this says asymptotic significance. That's the same as a p-value. So, and they're assuming a two-tailed test, as we always assume, unless otherwise told. So 0.124, what do I do with that? Remember our adage, if the p is low, the null must go, and low is defined as being less than alpha, and alpha is always 0.05 unless we say otherwise. So is 0.124 less than 0.05? No, it is not. Therefore, the null does not go. Therefore, we retain the null or fail to reject the null. Therefore, customer satisfaction is not related to employee empowerment. Same thing, much faster done as doing it by hand. There's a note here. The note here is that there are 0 cells which have an expected count of less than 5. SPSS does that for you. It says it did the math and it looked at all these cell values and figured out what the expected numbers were, and wanted to tell you if anything is less than 5, because if it's less than 5, it violates one of the chi-square assumptions. Here, nothing violates the chi-square assumptions, so we're good. We're good to go. Now, it also gives you additional tests. Here we got the chi-square value at the top, something called a likelihood ratio. Don't worry about that. We don't do that in this class. Then we got the Fisher's exact test. Right? After that, we have a linear bilinear association. Don't worry about that. We don't do that in this class. But look at the Fisher's exact test again. That's the one I said is very similar to chi-square, and it's actually better than a chi-square. It's just more complicated. And it found a p-value of 0.142. Look at these columns. The first column here is the asymptotic significance again, what we had last time. The second is the exact significance for a two-tailed test, and then an exact significance for a one-tailed test. Anytime we have an exact value, that's better. Clearly we want two-tailed tests, so exact is always better. So we look in this column here. The Fisher's exact test gives us a p-value of 0.142. That's a better estimate of whether or not there is a relationship between customer satisfaction and employee empowerment. But it gives us the same answer. The p is not low, the null does not go. Same answer. So why do we do this if we have this? Again, the answer is because we didn't have computers back in the day. And because we didn't have computers, we'd have to do it by hand, and this was easier to do by hand. The chi-square is easier to do by hand than the Fisher's exact test. But we have computers, so we do the exact test when we can. Okay. Moving on. Let's say that one of our cells had a 0. This is in our original data. Right, here it is. So I replaced one of our data points with a 0 instead of a 5. So suddenly I violated that number one assumption that the observed values, the cell counts, can't be less than 5. What happens then? Well, I get a p-value of this, which is highly significant, saying, yeah, get rid of that null. You get out of here, null. You got to go because your p is low. You know how that works, right? And I'd be very happy. But is that valid? No, it's not. It's not valid because I violated the assumptions that make the chi-square so good. So what do I do then? Well, if you guessed Fisher's exact test, you are correct. So if I violated the first assumption of chi-square, which is the observed cell counts must be at least 5, I look at the Fisher's exact test. And guess what? It's also significant. So it was right all along. Fantastic. Okay. So in that case, the Fisher's exact test gets us out of the mess. Now, let's say I had 2 of them instead of just 1 that were 0. And that gives me a result like this. Suddenly, one of the expected cells is less than 5. So in this bottom box here, when it shows me the chi-square test, it has a little subtext over here, A. It says that one cell has expected counts of less than 5. SPSS has told me, hey, look out, you're violating one of the chi-square assumptions. And that is that, well, first of all, 2 of them have observed cell counts that are less than 5, but also one of the expected counts are less than 5. Notice it doesn't tell me that the observed are less than 5 because it assumes I know that, because I entered that data. I should know if it's less than 5 or not. But it's telling me that one of the expected numbers is less than 5. This is when I would usually apply a Yates continuity correction. Remember though, Yates only applies in a 2x2 or 2x1 scenario. I've got a 3x3 here, so I can't apply the Yates continuity correction. Even if I could, I wouldn't bother, because Yates really is made for people who haven't got computers. I've got a computer, so what can I do? I can do a Fisher's exact test again. So again, the Fisher's test tells me it's significant, so yay. So bottom line there is, I can always do a Fisher's exact test in real life, because that's always better. But when doing things by hand, there are certain assumptions for chi-square we have to do. Now, a lot of computer programs, when the sample size is very large, and you tell it to do a Fisher's exact test, it might still do a chi-square just to save on processing time, because it ends up being the same thing. So there's that possibility as well. Oops. Back up for a second. Now let's talk about two other tests, and you're not responsible for doing these tests. I just want you to know what they are and when you would use them. The first is the MannWhitney U test, and this is the non-parametric analog of an independent group's t-test. Ouch, what does that mean? It means that if you've got ordinal values, like a Likert scale, like the one we just did, satisfaction is low, high, very high, that's an ordinal scale, then we can use a MannWhitney U test if in fact we are dealing with two population distributions. So this is the output of a MannWhitney U test. It's the same kind of deal. It gives you a significance number down here, 0.049, whatever it might be. Don't worry about this slide too much. I pulled that out of a textbook manufacturer. There's a lot of stuff here I haven't really talked about in class. It'll probably confuse you more. Just focus on the fact that MannWhitney U test is great for ordinal values and two groups. On the other hand, we have a Koskalwallis test, which is the non-parametric analog of a one-way ANOVA. So that's where we're comparing essentially ordinal values across more than two groups, 3 groups or more. So back up for a second here. Oh, so slow, come on. The test statistic for a Koskalwallis test is the H statistic. Remember, for the t-test, we have the T statistic. For the ANOVA, we have the F statistic. For the chi-square, we have the chi-square statistic. And for the Koskalwallis, we have the H statistic. Everyone's got to have their own statistic. I don't know, maybe there's brownie points somewhere. I'm not sure. But again, I don't require you to know the distribution of the H statistic. Just know that it exists, right? So all these different tests rely upon a different kind of test statistic that usually relates to a distribution of some kind. So this this table here summarizes what I'm talking about. If we have nominal measures, what we typically have, like male or female, or disease presence or disease absence, or Ontario residents versus Quebec residents, and we got two groups, we can use a chi-square test. If you got 3 groups or more, we can use a chi-square test too. Chi-square is great for nominal measurements. On the other hand, if we have ordinal measures, we have the MannWhitney U test for 2 groups and the Koskalwallis test for 3 or more groups. So in the example we just did with customer satisfaction and employee empowerment, that was 3 or more groups, and it was an ordinal scale. Even though we did a chi-square test, we should have done a Koskalwallis test. And again, I don't require you to know how to do these. Know that they exist. And in a future course, you can learn how to do them, or learn yourself, because it's not that hard. In fact, SPSS will do it for you. So remember, a chi-square cannot be used to test whether related groups are associated. Meaning, if I've got husbands and wives, or twins, or people that I know have some sort of systematic relationship, it's not appropriate. If I'm doing a match study of some kind, a chi-square is not appropriate. If we have a relationship, we're going to use something called a McNamaras test, invented in 1947 by Quinn McNamara. If you care, it's not really relevant, but some people like history. And I like pointing out the fact that it's less than 70 years old, because all this stuff is new. It's still evolving. And as computers get more powerful, all this stuff will fall into the background, and we use more complicated approaches. But I'll show what a McNamaras test looks like, because I think it's a useful thing for you to know. And yes, you are responsible for the McNamaras test. Here's an example. We have 50 women, and they are going to take an education intervention, a seminar on breast cancer awareness. And we're going to ask them before the seminar and after the seminar, do you do self-examination, BSE, breast self-examination? So beforehand, some will say, oh yeah, I do it, and some will say, no, I don't. They'll take the seminar, and then a few months later we'll ask them, hey, do you do it now? And we're going to see whether or not the seminar has in any way changed their breast cancer self-examination behavior. Clearly, this is fantastic for evaluating programs. Now, you can probably see that the two groups are related because they're the same people. I'm asking the same women before and after. Did you do this? That's more than a systematic relationship. They're the same people. I could have done the same thing with husbands and wives. Ask the husbands beforehand, does your wife do breast cancer screening? And then after the seminar, ask the wives, do you do breast screening? And it'll be something similar that way. That's kind of a stupid thing to do, though. I'm not sure why we do that. But you can see that the systematic relationship matters. So clearly, McNamaras test is great for evaluating interventions or programs like that. This is how you set up the contingency table for McNamaras test. It's a little different than the other tests. This is actually a 2-by-1 table in some ways, but look at it carefully here. So we got those who did the screening before the intervention and those that are after the intervention, and we're looking to see where they overlap. So 15 people were doing it before and did it after. They didn't change their behavior. 30 people weren't doing it before, but they were doing it after. That's great. We like those 30 people. That's who we're looking for. If I just looked at that 30 and reported that to my funders, saying, you know what, 30 people changed their behaviors as a result of my study, right? So 30 out of 45, or out of 50 rather, that's a lot. 60% of people changed their behaviors. Now, that's not the full story, though, because 15 didn't change their behaviors, and 5 weren't doing it before. I'm sorry, I said that wrong. Sorry, 30 weren't doing it before, and 30 still didn't do it before. That's bad. That's bad, bad, bad. So in fact, that's horrible. 30 plus 15, 45 out of my 50 people didn't change at all. That's horrible. It's the 5 here that we cared about. So 5 weren't doing it before, but they were doing it after. So as a result of my intervention, 5 people changed their behaviors. That's not very good. So we know that going into this analysis that we're not going to find good things here. But now we're going to prove it anyway, statistically, just to make sure. If I just report those 5 people and say, you know what, out of my 50, 5 people changed their behaviors, 5 out of 50, right? So 10% of my sample. And you can argue, hey, 10% is better than 0, whatever it might be. So let's do the math. The null hypothesis is that there is no relationship between receiving the educational intervention and whether or not you practice BSE. In other words, the intervention does not work. That's the null hypothesis. The workshops are pointless. And we want to be able to either reject or accept that null hypothesis. Let's do the math. It's very simple. This is the formula for McNamaras test. It's a different way of computing chi-square. It's still a chi-square value. We're still going to use that chi-square number and compare it to the back of the book. We're just going to compute it differently, and we use it this way. So if you set up your table like this, it's just the difference between these diagonals, the absolute value of that difference, minus 1, you square it, and you divide it by the sum of these two. So we care about the discordant pairs here. All right? So just remember that, and we look it up in the back of the book, we figure it out, we get 3.2, and we compare it to the value of the back of the book. But we need degrees of freedom. What's the degrees of freedom here? It's 1. So it's number of rows and number of columns. 1 times 1 is 1. The value of the back of the book is 3.84. We fail to reject the null. Not surprisingly, because we already saw only 5 people out of 50 changed their behaviors. Therefore, we fail to reject the null and conclude that there is no relationship between this workshop and women's behavior when it comes to self-examination. In SPSS, this is called the McNamara-Boker test, if you want to try it out, so you can play with it if you like. And you can look at more examples here of McNamara's test on that link. So that is the extent of the presentation. I'm trying to get back here. Stop presenting. Oh, Kanibaraka. So I'm back in front of you now, showing off my horns. I got no questions on Twitter, so I assume everything's clear. Was it? Was it clear? And that was a very fast lecture. 36 minutes. I have 9 viewers total I'm looking at. So clearly people got bored and left. Screw you. It's fascinating. This is entertaining. That is all. And I will see you in class on Friday.